Good evening, everyone. We'll start in a couple of minutes. We'll wait for some more people to join and then we'll start. Hello, everyone. Good evening and welcome to week 6 of the live interactive sessions for the course on Integrated Waste Management for a Smart City offered through NPTEL. And my name is Sethi Vinayagam. I'm a PhD scholar in the Civil Engineering Department at IIT Madras. We'll start with the overview of the lectures covered in week 6. So we started with the vehicle routing problem. Actually, vehicle routing problem was started in the last lecture of week 5. So that was continued in this first lecture for week 6. And once we saw the vehicle routing problem, we then moved on to how to design a collection system. And then in the second lecture, we looked at a numerical example for this collection system design. So we looked at various factors from what will be the pickup time, how to determine the pickup time, how to determine the volume of the trucks, and how to determine the number of personnel needed for the collection, and so on. And once we looked at that, we then reviewed the state of waste management in 6 cities. So which are we looked at what are the techniques being followed in these different cities. So these cities varied in terms of the amount of waste that is generated, so from 4,000 tons to 200 tons or so. So we looked at different size of cities, and then we looked at what are their future action plans. And then in lecture 29, we looked at the biochemical process. How do we, which is basically how do we convert the organic fraction in solid waste into a stabilized form with the help of microbes, right? So we looked at the aerobic process, which is the composting process, and then the anaerobic process or the fermentation process. Then we looked at aerobic composting in detail, and then we had two additional lectures. So lecture 30A was about the impact of COVID-19 on the solid waste management. So how it affected the different aspects of solid waste management. And then in the second additional lecture 30B, we looked at the World Bank report on called Water Waste, the second version 2.0, which basically gave us a summary of what is the status of waste management across the world. So in different regions, how are the things standing before the COVID times, right? So that was the overview of what we learned in week 6. So with that, we'll move on to the problem solving session for this week. So the first question is, which of the following component is destroyed during the biological treatment of municipal solid waste? So the options are residual volatile solids, biological volatile solids, Inorganic, none of these. So when we talk about municipal solid wastes, it has a varied composition. There are multiple components which make up the municipal solid waste, and here we are talking about the biological treatment. So when we are talking about biological treatment, so we are concerned with the organic fraction, right? So only that will be that can be processed by the biological treatment, which is the microbes like bacteria, fungi, and other things. So that's what we mean by destroyed. So it is to process those organic fraction. So if you look at these options, so out of the residual volatile solids, biological volatile solids, and inorganics, the one that can be processed or destroyed by the biological organisms is the biological volatile solids. So the correct answer is option B. So this is from the lecture, if you recall it. So we have these different components. We have water, which is the moisture content. The inorganics. The inorganics can or the examples are like glass, metal, dirt, and other inorganic parts. So these will not. This will not be processed by the microorganisms. And then we have the biological volatile solids and the residual volatile solids. Both are biodegradable. However, it is only this light blue part, which is the biological volatile solids, which will be acted upon by the microorganisms, whereas the residual volatile solids will still remain as such in that waste stream, right? So only it is the BVS that will be destroyed by this biological process. Okay, any questions on this question? Okay, so let's move on to question number two. Uh, Here we have two columns. So the first column tells us different components, and then the second column tells us different conditions which can be used to determine these different components. So the question is to match the parameters or the conditions with their corresponding descriptive determination procedures. So the options, different matches are given here. So we can take a minute to think about it, and then you can answer which is the correct matching given here. So we have different options. So the volatile combustible matter, water content, and fixed carbon, and the different techniques that can be used are one is lost when heated to 105 degrees centigrade for 1 hour. Second one is combustible residue that remains after the volatile matter when at the temperature of 550 to 950 degrees centigrade. And the third one is ignition at 450 degrees centigrade. So you can take a minute to think about how which procedure will be used to determine which parameter in the first column. I'll create a poll, and then you can post your answers in the poll. Okay. I have launched the poll. You can, once you are ready with your answers, you can put it in the poll. Okay, we have one answer for option C. Okay, we'll give another 15 to 30 seconds, and then we can look at the answer. Okay, so let's take a look at the answer now. So the correct answer is actually C. That is correct. So what do we mean by approximate analysis? So approximate analysis will tell us for or different or in a broad sense, it tells us what is the composition of the waste, like in terms of what is the water content, what is the volatile combustible matter, how much there is the fixed carbon, and how much non-combustible residue or the ash is there in a particular waste. Right, so we have standard procedures that we can use to determine this. So for water content, the procedure is to heat it to 105 degrees celsius for about 1 hour. Right, so water is the first thing that will be leaving the waste. Right, so it will water will boil at 100 degrees centigrade. Right, so when we do it for 105 degrees centigrade and do that for 1 hour, so all the water will be lost. Right, so with that we will be able to determine how much water was there by weighing it before and after doing this heating. So the second one is the volatile combustible matter. So once we heat it to 450 degrees centigrade, whatever is the volatile matter that will leave the waste. Right, so then what we mean by fixed carbon is whatever is not whatever is left there. So whatever is not uh, volatile is the fixed carbon. So for that we need to heat it to even higher temperature. So that is for 550 to 950 degrees centigrade. So in that temperature it will combust, and whatever is the residue that is left is the fixed carbon, and the non-combustible residue, whatever is finally there, that is the ash, and we can find out that at the end. So that is the proximate analysis that we will do. The other type of analysis that we could do is the ultimate analysis. So where our interest is to find much more detailed much more detailed analysis, where we look at how much carbon is there, how much nitrogen, hydrogen, and so on in terms of individual elements. Whereas in the proximate analysis, we look at these broad components. So with that, if we do the correct matching, so volatile combustible matter is ignition at 450 degrees centigrade. So that is 1 with 3. Water content is lost when heated to 105 degrees centigrade. So 2 with 1, and fixed carbon is the combustible residue after the volatile matter, which is 550 to 950 degrees centigrade, that is 3 with 2. So that is given in option C. Any questions? Okay, so we'll move on to question number 3. Which of the following compostable material has the highest carbon to nitrogen ratio? Options are cow manure, yard waste, digested sludge, and newspaper. So when we talk about carbon to nitrogen ratio, we are not talking about which has the highest carbon or the highest nitrogen, or like that. We are not talking about the individual individual elements quantity in these material. We are talking about the ratio, right? So the ratio has to be highest. So for this ratio to be high, two things needs to be there. One, it can be due to high amount of carbon and low amount of nitrogen. Because this is a ratio, when the numerator, the carbon content is higher and the nitrogen content is lower, the ratio, carbon to nitrogen ratio, will be higher. Right, so large numerator, small denominator. So when we look at these four components, out of these the newspaper has the highest carbon to nitrogen ratio. It is option D. So we looked at some of these in the lectures. So we saw that the digested sludge has one of the lowest ratios of 15 is to 1, whereas the yard waste has a relatively high 40 is to 1 to 80 is to 1, but it is not as high as in the case of newspaper, which has a range of 175 is to 1 to 800 is to 1. So it has a very high ratio of carbon to nitrogen. Right, so because it is high in carbon and low in nitrogen, because of this combination, we have a very high ratio of the carbon to nitrogen in the newspaper. Right, is that clear? Okay, so the answer is newspaper, which has the highest carbon to nitrogen ratio. Question 4 is what should be the range of moisture content on a wet weight basis of waste for composting? So the options are 10 to 30%, option B is 50 to 60%, option C 45 to 80%, and option D is 20 to 30%. So for composting, moisture is one of the factors that affects the composting process. So there needs to be a certain amount of moisture content, which will make the composting process effective or efficient, right? So there needs to be some amount of moisture content. So this moisture content is so the optimal value for this is determined on a wet weight basis. So what do we mean by wet weight basis? It is the moisture content is calculated along with so by considering the weight of the waste along with the moisture content. We do not dry the waste and then determine this value. When the moisture has is present in the waste, in that state we determine what is the moisture content. So the optimal value that is given is 50 to 60 percentage, right? So when there is about 50 to 60% of the total weight is the moisture, then it is ideal for the composting process, right? And how can we achieve this? So we can achieve this by adding sludge. Sludge will contain some moisture. By mixing the waste with the sludge, we will be able to introduce moisture into the waste, right? But the moisture should not be too high. Why it should not be too high? Because we also need some oxygen. So the oxygen comes from the air that is supplied for this composting process. So if we have too much moisture, more than this 50 to 60%, what happens is all the pores or the open spaces that is available within this waste will be clogged by all the water. So in that case, air cannot penetrate through the waste. So that will not give sufficient amount of oxygen for the decomposition to take place. Therefore, it should not be too low and it should not be too high. So a range of 50 to 60% is ideal for the composting or the aerobic process. Okay, any questions? Why it should not be too high or too low, right? Okay, so moving on to question number 5. So this is about the waste collection. So this is a numerical problem. So here we are given the pickup time per trip for a waste collection vehicle as 2.7 hours. Okay, and then the at-site time per trip is 0.4 hours, and we have to complete the round trip in 4.1 hour. So what would be the haul time allowed per trip in hours? So the options are 1.5, 0.7, 1, and 0.5. Right? So we need to so we have different components when we are talking about the collection in terms of the time spent. So we have the pickup time, and then we have the at-site time, we have the round trip time. So the one missing component here is the haul time, which we need to determine. So you can take 1 or 2 minutes, and I'll create a poll in the meantime, and then you can answer in the poll. So if the question is not clear, please let me know. I can explain it again. The poll is launched. Once you are ready with your answers, please answer the poll. Okay, has anyone completed it? Any answers from anyone? Okay, so we'll look at the answer now. So before that, we'll try to first understand what is being asked in the question. Okay, okay. So consider this illustration here. So we have some residential area, right? So we have a pickup truck. So that starts at the garage, and then in the morning it goes to this residential location, right? So it takes some time. That is T1, the time to travel from the garage to the residential area. And then there are multiple houses in this area, so it takes some time to collect the waste from each of these houses, right? So we have to go to each house, and then at each house it takes some time to get the waste into the truck. So the sum of all these times spent in collecting the waste from all the houses is called the pickup time. We call this as PHCS, right? So it is the pickup time. So it is the sum of all these individual times spent at each house. So once we have collected all the waste, we have two options: either we go to the landfill or to the transfer station. So whatever is the case, so the time that is spent once we have collected the waste, and that to travel to either to the landfill or the transfer station, whichever is the case. So that time spent in that particular component is the haul time, H, right? So we are hauling the waste from the residential area to the destination, which is either the landfill or the transfer station. So that is the haul component, haul time component. So this, and then once we drop the collected waste at this destination, we have to come back again, because we may not have collected all the houses. So some, because the vehicle capacity is limited, we may have to come back to the residential area and then collect the waste again from the houses which were not served in the first trip, right? So again we come back, so that is also included in the haul time. So the time to and fro from the residential area to the destination is the haul time. So both from the forward and the reverse direction time together is the haul time, right? And this totally is called the round trip, because we are starting from the residential area, going to the landfill or the transfer station, and then coming back to the residential area. So that is called as the round trip. So we have different components, which is the pickup time, which is the time spent in the collection. Then we have the outside time, which is the uh, time spent to empty the vehicle at the landfill or the transfer station. All the collected waste has to be dumped at these two, either of these locations, right? So that time is called the outside time. And once we have dumped it, we have to come back. So which is also in the haul time, right? So we'll see how to now solve this. Okay, so let us say capital T is the round trip. time. So the round trip time is made up of three components, which is the P or the pickup time, and then there is the outside time, let us call that as capital S, and then there is the halt time, let us say that to be capital H. Okay, that so the round trip time is made up of three different components: the pickup time, the outside time, and the halt time. So out of this we are given three things. We know capital T, which is 4.1 hours. We know capital P, which is 2.7 hours. We know capital S, which is zero point 0.4 hours. Right. So with that, we will be able to determine what is capital H. So it is nothing but T minus P minus S. Right. So that is 4.1 hours minus P is 2.7 hours minus 0.4 hours is the outside time. So capital H or the halt time is equal to 1 hour. Okay, so that is option C. Okay, is that clear? How we determine the halt time? Any questions? So when we are talking about the round trip, we are not interested in this T1 and T2. So this T1 and T2 happens only at one time in the day. So when in the morning there will be T1 when the truck leaves from the garage to the residential area, and then at the end of the day when it goes back to the garage, the time taken is T2. Right. So these two components take place only once. But in this problem, we are not interested in this T1 or T2. We are only interested in the round trip, right? So which is only containing these three components. Okay. Any doubts? Okay. If there's no doubt, we'll continue. And okay, question six is about how do we determine the optimal mixture, right? So we saw that for composting process we need certain moisture content and certain optimum level of carbon to nitrogen ratio. So how do we determine how much of the sludge has to be mixed, right? So the question is, to obtain a carbon to nitrogen ratio of 40 is to 1, how much sludge has to be mixed with 1 kilogram of leaves? Okay, that is the question. So we are given some information. The carbon and the nitrogen content in 1 kilogram of leaves are 0.35 kg and 0.007 kg respectively. And the carbon and nitrogen in 1 kilogram of sludge are zero point 0.2 kilograms and zero point zero 0.04 kilograms respectively. Right. So given this individual amounts of carbon and nitrogen in both 1 kg of leaves and 1 kg of sludge, we need to determine with for 1 kg of leaves how much of sludge has to be added so that the mixture will have a carbon to nitrogen ratio of 40 is to 1. Okay, so the options are zero point 0.3, 0.08, zero point 0.2, and 0.05. Again, you can take a minute or two to calculate it and then answer in the poll. If you have any doubts, you can unmute yourself and ask at any time. Okay, the poll is launched. Please take a minute or two to solve it and then answer it. Okay, any answers before we look at the solution? Okay, so the answer is already displayed there. It is option D, which is 0.05. Okay, so we'll take a look at how to arrive at that answer. Okay, so the question is, what should be the amount of sludge that is to be mixed, right? So that is our variable. We don't know how much. So let us just assume that X kilograms of sludge is mixed with 1 kilogram of leaves. Okay, let's just assume that we don't know. Now, once we have mixed some x kilogram of sludge, how do we determine the carbon to nitrogen ratio in that mixture? So we need to know what is the total amount of carbon in that mixture, and we need to know what is the total amount of nitrogen in the mixture, and then the ratio of those two quantities will give us the carbon to nitrogen ratio, which we know should be 40 is to 1. Okay, so we know the uh, target carbon to nitrogen ratio is equal to 40 is to 1, and that is given by the total carbon in mixture is equal to what we know. 1 kg of leaf is there in the mixture, and in 1 kg of leaves there is 0.35 kg of carbon. Okay, so that we know, plus in 1 kg of sludge there is zero point 0.2 kg of carbon, and in x, so therefore in x kg of sludge there will be x times zero point 0.2, which is 0.2x kilogram. So this is the total amount of carbon in the mixture, and similarly we will be able to find the total nitrogen in the mixture, right? So that will be what, 0.007 kilograms in 1 kg of leaves, right? And then in x kg, there will be x times 0.04, which is 0.04x. So this is we know the total carbon and the total nitrogen. So the ratio of carbon to nitrogen in the mixture. So carbon to nitrogen ratio in the mixture is what is the ratio of these two quantities, right? So it is 0.35 plus 0.2 x divided by 0.007 plus 0.04x. So this is the carbon to nitrogen ratio in the mixture, and we therefore we need to find x now. So how do we find x? We equate this to the carbon target ratio, which is 40 is to 1. We know that much should be there. So this should be equal to 40 by 1. Okay, so if we just solve this particular equation, we'll be able to get it. So what we will get, we'll get 0.35 plus 0.2x equal to 0.007 into 40. So that will be 0.28, right? Yeah, that is 0.28 plus 0.04x into 40. That will be around 1.6 x, right? So by rearranging this and solving it gives us that x is equal to 0.05. Okay, so that's how we find out what should be the amount of sludge that has to be mixed with 1 kilogram of leaves, right? So 0.05, the unit is kilogram. So the 0.05 kilogram of sludge should be mixed with, for every 1 kg of leaf that is present in our waste, we have to add that much, for every kilogram we have to add 0.05 kilogram of the sludge, so that the final carbon to nitrogen ratio will be 40 is to 1. Okay, is that clear? Any questions? Okay, okay, let's continue. So question 7 is, To minimize the loss of nitrogen as ammonia gas NH3, pH must be below which value during composting? Okay, the options are 8, 5, 8.5, and 7. Right. So during composting, the pH varies, right? So at different stages of the composting process, the pH level will be different, right? So we start at some value, and then when the composting begins, so there will be some acid generation, and that will lower the pH value. And then in the later stages, so the pH value will again rise, so it will go beyond the neutral, and it become more basic once. But when it goes beyond some value, so the nitrogen present in the waste will be converted to the ammonia gas, right? So that will remove the once it becomes the ammonia gas, it will leave the system, right? So we will be losing nitrogen, and therefore our carbon to nitrogen ratio will be affected by this, so the composting process will be affected. So to prevent that, we must maintain the pH value. So there is a value of pH which should not be crossed, and that value is 8.5, right? So this was covered as one of, when we looked at the different factors such as temperature and so on. So pH was one of the factor that we covered in the lectures, and we saw that the value of the pH should be less than 8.5. And to achieve that, we can use processes such as aeration, so that will help us to maintain the pH. And whereas some other process such as addition of lime will not help, because those will increase the pH of this waste or the digested sludge, which will only accelerate this process of losing nitrogen as ammonia, right? So that is the answer. It should not cross 8.5. Similarly, on the other side, it should not drop less than 4.5 as well. So there is a range of pH which is desirable to have in the during the composting process. Okay, so question number 8 is, which of the following statements are true for designing the pickup routes for Indian cities? So the options are no U-turn. Option B is U-turn is preferred. Option C, both right and left turns are equally preferred. And option D is right turns are preferred. Okay, so we need to say which of these are correct for the Indian context, right? So first, the C and D are about turns, whereas A and B are about U-turns, right? So with respect to U-turns, we do not prefer U-turns, right? So we don't want U-turns when doing the collection, because U-turns will be more time consuming. So our streets are generally narrow, right? In the local streets are generally narrow. So making U-turns, the maneuver is also difficult, and even if you have wider streets, U-turn will still take a lot of time to perform. Considerable amount of time will be lost when we are doing the U-turns. Therefore, we do not prefer U-turn. And with respect to the turns, left and right turns, so option C says both are equally preferred, but that's not the case. We prefer one type of turn more than the other, and D says the right turns are more preferred. Actually, both C and D are wrong. In the Indian case, left turns are more preferred. Why? Because when we take a left turn, it's much easier because we are not interacting with the oncoming traffic. So the traffic that is opposing our movement is not in. We are not interacting with that when we are making a left turn. Whereas when we are making a right turn, we have to cross the oncoming traffic and then go to the other direction, right? So there is more chance of collision, and so right turns are less preferred in our case, whereas left turns are more preferred, right? But the guidelines are generally designed for the US systems, so where they drive on the right side of the road. So for them, it is the right turns which are more easier than the left turns, right? But in our context, left turns are more preferred. Therefore, options B, C, and D are wrong, and only option A is correct, right? So we saw that in the vehicle routing problem that we do not prefer U-turns. And here, though it is given right turns are preferred, it is based on the US guidelines, which is for the right driving traffic. Whereas the question here is about the Indian cities, so therefore this should be left turns are preferred for us. Okay, any questions? Okay, if there are no questions, okay, we'll move on to question number 9. So here we are given a physical composition and the moisture content of the different components of a collected municipal solid waste as given in this table. So we have paper, we have cardboard, cloth, newspaper, and some other compostable material. So we have different percentages of these components in this mixture. There is 20% paper, 15% cardboard, 3 percentage cloth, 30% newspaper, and 32% of other compost material. And these different components have different moisture content within them. So 5%, 3%, 3%, and 55% for these different components. So the question is, we need to calculate the moisture content of the waste. So these of the mixture of these different components, right? So individually we know their moisture content. Once they are mixed in this different percentages, what will be the moisture content of that resulting mixture, right? So that's what we need to find out. So the options are 20%, 30%, 15%, and 40%. Again, you can take a minute or two to solve it and answer in the poll. The poll is launched. If you're ready with your answers, you can put them in poll. Okay, we have one answers for option B. Any other answers? Okay, so we'll look at the answer now. The correct answer is actually option A, 20%. So we'll see how we arrive at that. Give me a minute. I'll switch to. Okay, so let us see how to solve it. So we need to know what is the moisture content of the mixture, right? So that is, we have different components, and we know the individual moisture content, and we also know the percentage of these different components. So all we need to do is take a weighted average of these moisture contents, and the weightage is nothing but the percentage content of these different components. So it is sigma over I. So I represents the each individual components, that is a paper, cardboard, cloth, etc. So for each component, we just take the product of Wi. So the weightage is nothing but the percentage multiplied by the moisture content of that particular component I divided by the sum of all the weights. So sigma over I W, right? So this weighted average will give us the moisture content of this mixture. But we can ignore the denominator because the sum of all the percentage is equal to 100% or 1, right? Therefore, the denominator can be ignored. So just the numerator needs to be evaluated, right? So what will that be? It will be 20%, which is zero point 0.2 into 5, right? So 5% is for paper. Then for the second component, it is 15%, so 0.15 into 3. The third is cloth, which is 3%, 0.03 into 4, plus newspaper is 30%, so zero point 0.3 into 3, plus other materials are 32%, 0.32 times 55, right? So if you solve this, you'll get the moisture content as 20%, right? So this is nothing but a weighted average, right? So we are just taking the different percentages, and those percentages are the weights, and then we multiply that by the corresponding moisture content, and that weighted sum will give us the moisture content in the final mixture. Okay, any questions? How we calculate for the mixture? Let me just quickly check the calculation. It is 20% of 5, 15% of 3, 3% of 4, 30% of 3, and 32% of 55, which is, yeah, around 20.07%. And the closest option is a 20, right? So we go for the closest option. So it is 20%. Okay. So let's continue. Question 10. So we are moving into the multiple select questions from now on. So more than one answer, one option could be correct. So which of the following types of solid waste can be biologically treated? So the options are yard waste, agricultural waste, municipal solid waste, and construction and demolition waste. Okay, so when we are talking about biological treatment, so we need to remember that we are dealing with the organic material, right? So the organic fraction of the solid waste, only those can be biologically treated. So what we have to look for is which of these type of waste contains some organic matter, right? So we have yard waste, which is nothing but the garden waste, all the leaves and so on. So that is organic, right? So it can be biologically treated. Agricultural waste, again, it is organic waste. Municipal solid waste, it contains food waste, right? It can contain other wastes as well, like plastics, glass, and so on. So it has both the organic component as well as the inorganic fraction, but still it contains those organic components, so it can still be biologically treated if we separate it out, right? So but D is construction and demolition waste. It is not it does not contain organic materials, therefore it cannot be biologically treated. So therefore the correct options are A, B, and C, right? So we saw this. So municipal solid waste, sewage sludge, agricultural waste, even industrial waste, if it contains the organic fractions, and also hazardous waste if they contain, right? Generally we don't see them, but the municipal waste, sewage waste, agricultural waste, in always or in most cases will always contain some organic fraction which can be treated, right? So therefore the correct options are A, B, and C. Okay, any questions? Okay, so moving on to question number 11. Which of the following components of the municipal solid waste can be treated by a biological treatment process, right? So we are now talking about individual components. So the options are plastics, option B is paper, option C is cardboard, and option D is food waste. Again, we'll have to apply the same logic, right? We have to look at which of these are organic, which of these contain organics, right? So plastics doesn't is not biologically it's not biologically degradable, whereas paper, cardboard, as and food waste, all these can be degraded biologically. There'll be different time it takes for treating these, but they can still be treated biologically because they have some organic content, right? So all options B, C, and D are are candidates for biological treatment, right? We saw paper, cardboard, food waste, yard waste, and even but theoretically, wood, leather, and rubber also can be biologically degraded, but it takes more time for any practical applications, right? So we cannot wait for that long. Therefore, we generally do not use wood, leather, and rubber in the composting process. So we need relatively quickly, we need these to be degraded, right? So that we can use that for manure and other things. Therefore, the options are B, C, and D. So the time is also an important component for any practical application. Okay, so moving on to question number 12. So this is about the aerobic composting. So which of these followings are generated during the composting process? So the options are SO42 minus sulfate, B is carbon monoxide, C is water, and D is nitrate, NO3 minus. So we can use the chat because this is a multiple answers question. So, which of these do you think are generated during the composting process? Okay, there is a question in the chat. Do we consider the following for the biological treatment or not, like wood and rubber? So, as I said, they can be biologically treated. However, since they take a long time to degrade, we do not generally use them for the biological treatment because we have to wait for a long time, right? So that is not practically feasible for us, right, to wait for a long time for this to degrade and then use the end product. Therefore, we generally avoid wood and rubber, but they can be biologically degraded. Okay. For this one, you can again use the chat to answer it. So, which of these will be generated during the composting process? Any answer? We looked at the aerobic process in one lecture, right? So there, this was discussed. And so if you remember, so one thing you can easily say out of these four options, at least one you can easily identify that that will be generated. Okay, we have one answer A, C, and D. Any other answers? Okay, so A, C, and D is in fact correct. So water, I think everyone knows, right? So water is one of the end products of the composting process. But in addition to that, we also have nitrate as well as sulfate, and we have carbon dioxide being generated. So here, but one of the option is carbon monoxide. So we do not get carbon monoxide, we get carbon dioxide. Therefore, we left option B out. But other than B, we have all other three options A, C, and D being generated, right? So and along with that, we also get some heat because this aerobic composting is an exothermic process. Okay, so with that, moving on to question number 13. Which of the following statements are true for the windrow composting? So the options are temperature is usually maximum in between 5 to 15 days of composting. Option B is temperature is usually maximum after 20 days of composting. And option C and D are about the pH. So pH is usually stable between 7.5 and 8.5 during the end phase. And D is it is stable between 7.5 and 8.5 during the initial phase. So we have to first look at temperature and when it is high, whether is it high in the initial period or in the final period, and then pH when it is stable. Is it stable in the end phase or in the initial phase? So there can be two correct options for this. Again, you can use the chat to answer it. Okay, we have one answer, B and C. What about others? Do you agree that B and C are correct, or you think some other combination is correct? Okay, so we look at the answer. So actually, it is A and C, right? So the temperature is usually maximum in between 5 to 15 days. So temperature is higher in the starting period, and the pH is stable at the ending period, right? So initially, the pH will vary significantly, but it will stabilize between 7.5 and 8.5 in the end process. So this is an illustration, right? So we have the results from the study. So how it will change. So for the windrow composting, so we'll first, so the left y-axis shows us the temperature, and the right y-axis shows us the pH value. So first, if you look at the temperature first, so the y-axis shows the period or the time spent in the composting process. So initially, the temperature is lower; it increases to and reaches a maximum value in the initial phase between the 5 and 15 days, right? So that is the period when the temperature reaches a maximum, and then with time the temperature goes down, right? So it is maximum in the 5 to 15-day period, right? Again, there is a range of temperature that can take place, right? So it depends on the mixture that we are dealing with. And if you look at the pH again, so initially the pH drops because of the generation of the acid component, right? So because of the generation of acetic acid, the pH will initially drop down, right? It reaches a minimum, and then after some time it will increase. The pH will again increase. So we saw that pH will increase after some time, and then it stabilizes. It reaches a range of pH, so between 7.5 to 8.5, right? So that is the range of pH, and this range is constant, or it is maintained for the rest of the period, right? So it is stabilizing at this range after or during the end phase, right? So the temperature is maximum in 5 to 15 days, and then the pH is stable at the end of this composting process. That's why the options we saw were A and C. Okay, any questions? Okay, so there are no questions. So this was the last question for this week. So if you have any queries, or you need any clarifications on any of the problems, you can ask. Otherwise, we can close the session if there are no further questions. So this we have completed 6 weeks. So we are in the midway of this course, right? So there are 12 weeks. So we have completed 6 of the 12 weeks. So half of the course has been completed. So if you have any questions on whatever we have seen so far, you can ask, or you can use the discussion board as well to post your questions. Okay, so I'll wait for a few more minutes. So if you have any questions, you can ask. If you have no questions, you may feel free to leave the call. We'll meet again next week. Thank you.